First speaker this afternoon is Tom Mendelson, who'll be speaking to us about task queues, particularly Celery, and where and when you may need to use them. Please make him feel welcome.
Hey everybody, as Mitch said, this talk is titled Task Queues, a Celery Story. I'm going to start with just a little bit about who I am. I'm a professional Python developer at a company called Polymathian. I actually work with Mitch. I sit opposite him, so thanks for the intro, Mitch. So Polymathian, we call ourselves a bespoke hosted mathematical optimization company. Basically what that means is we build tools that help big industry, usually mining, make better decisions and save them or make them money. I've been there for 2 3/4 years as of now. I'm also a 5th year software engineering student at the University of Queensland. And I love Haskell, but unfortunately no Haskell today. Python's pretty great too. All the details are on there. There's the Polymathian logo. All right, let's get into it. So this talk is going to be mainly in 2 parts. First of all, an overview of task queues themselves. And second of all, some specific task queue libraries for Python, as well as how we've used Celery and other libraries at Polymathian, and a few terrible jokes. So yeah, let's just dive right on in, starting with task queues more generally. What is a task queue? Task queues are queues of tasks. Crazy. What that actually means is there's a queue of messages where each message represents a unit of work or a task. And then these messages are distributed by a message queue, which we call the broker. Each of these are distributed to different processes, and those processes are called workers that actually do the work that the task describes. These are processed asynchronously, although you can, when you start your task, block waiting for it to finish. That little diagram there is just stealing AWS infrastructure diagrams. So we've got web servers, which are EC2 instances. Then we've got a message queue. That's Amazon SQS in this context. And that sends messages onto our workers that do the processing. It's generally pretty simple stuff, relatively easy to understand. So when might I want to use a task queue? So there are 2 fundamental requirements when you're using task queues. First of all is the work you're doing can be run asynchronously. And second of all, you're in a context where distributed systems make sense, because you've got to go out to your broker and back in. So they're all separate interacting systems. And what you get from this situation when you use a task queue, you get a degree of architectural flexibility. And the main benefit that I find with that is it allows you to make your architecture asymmetric. What I mean by that is your workers can be totally different to whatever is sending the requests for tasks to be run. Because we're in Python, we get extra stuff, which is actually an artifact of us having less stuff in the beginning. Task queues are really useful in Python for a thing called process-based parallelism, which I'll talk a bit on further. So basically, when you have async and a distributed system, you get some architectural flexibility. And you can see that that particular architectural flexibility is also asymmetric. Oh, skipped a slide. Yeah, so process-based parallelism. We're in Python land, and we've got a thing called the global interpreter lock. I call it the GIL. Some people call it the GIL. It's like GIF and GIF. In CPython, which is the normal Python interpreter, memory management isn't thread safe. So that means that when you change stuff, when memory is released, that if another thread's using it, there's no real guarantees. But we get those guarantees by adding locking with the global interpreter lock. And that says that only one thread can execute Python code at once. And that means that if you have high intensity, high processing stuff written in your Python, because only one part of that can run at a time, using threading to do things that have high computation in Python is pretty rubbish, and it's all run at once anyway, so a lot less useful. When you use task queues, you have your workers in separate processes, which means each separate process has its own GIL, which means that each process has one thread of execution in parallel. And so if you're able to distribute the work you're doing across these workers, then you still get all the parallelism benefits. It's just running in separate processes. Task queues happen to be a pretty nice way to coordinate this. So just some lingo, task queues provide message passing concurrency because you're passing messages, which is an alternative to shared memory concurrency, which you get when you're using threads in other languages like C and C++. So yeah, just some common use cases for task queues. User signs up to your system. You want to send them a registration or a validation email. It doesn't really make sense for them to wait on the web request to complete while you send them an email. So instead, you could spin up a task and send that to a worker, because you don't have to wait for that to complete. It just has to be done eventually. Other ones, generating image thumbnails. You don't have to immediately generate the thumbnail. People can download the full image until you've got a good thumbnail ready. If you're updating some complex and difficult to compute cached value, you can just update the cache over on the side and keep using the old one in most contexts. One use case we use is we generate reports, so Excel spreadsheets for stuff to download, and then data parallel workloads. So workloads where you do the same bit of work on a huge amount of data. You just chunk up the work and send it to different workers. So that's the process-based parallelism I was mentioning. There are some drawbacks. So starting a task is a lot harder than a normal function call, because you've got to write your message into a stream, and then you've got to send that over the network, and then you've got to pick that up on the worker, and then you've got to deserialize it, and then you've got to do the work, and then you've got to say, hey, I'm done. Basically, there's a whole lot of reporting that adds some overhead. So if you've got these tiny tasks that you could just do in a web request, please don't do them with a task queue. Second of all is state tracking. If you've got a lot of incremental progress going on, task queues aren't always the best approach. Usually, you can tell when a task is done or started, and that's about it. And you'd have to implement your own state tracking layer over the top. Realistically, what you want in this situation is to write your own worker system and just use a database to track the state. Task queues are for sending a quick message, picking up the message, and then sending a message back. If you use the database, you get to write your state, and you write any extra information because you want it to stay there. And then in Python, it's hard to serialize and deserialize some objects, for example, functions. So there are some use cases where you'd want to use a task queue where you can't. So basically, in short, task queues are great, but they're not magical secret scale source. They provide you architectural flexibility, but you still have to remember that there are drawbacks, and you need to know what you're doing. All right, enter Celery. Celery, like I say on the slide, is the standard in task queues. It's really simple for a simple use case. You literally just write Celery worker, and then suddenly you have a worker. And then on the other end, you go task.delay, and done. I'll show you a code sample in a second. It has a lot of features. And as soon as you start using those features, it really, really blows up in complexity. It's insanely powerful. There's so much you can do. There's like complex message routing features, task chaining, basically everything you could ever imagine, support for a bunch of different message brokers, support for storing results on different backends. There's a lot of features. It's really cool and really powerful, which is part of why it is the standard. And all of these features are really robustly tested, which is pretty great. So here's a code example. I'll actually be doing a few code examples throughout this presentation. This is what all of them are going to look like. So on the left-hand side, we have the shared code. So this is how you define, this is a task that I want to be able to run with my task queue. And then on the right-hand side, we've got a client function and a worker function. So in the client, you do add.delay 1 and 2, which says, I want my task queue to compute 1 plus 2 and get the result back. In Celery, result.get is blocking. So it sits there and waits for your task to complete, and then it gives you the result. Adding two numbers is a horrible way to use a task queue. Don't do this. This is a trivial example for demonstration purposes. But yeah, so all of my code examples are going to look like this. So cutting in, you've seen a tiny bit of Celery. Now I'm going to talk about Polymathian and how we used Celery. So like I said, we call ourselves an industrial mathematics company. We build optimization tools. And the way we use these is we build web apps. These web apps basically all have a very common workflow of input your data, configure some settings, click the run button, and it solves a really complex optimization. And then you get data visualization, and you get some reports to export. And you can do stuff with those reports. This isn't how all of our stuff works, but pretty much 90% of it does this. All of our software is deployed on AWS, and we kind of have this implicit goal of making use of AWS software wherever possible, although we do have some on-premise deployments, so it still has to be flexible. And then what actually makes us the big bucks is we have these really powerful optimization engines that solve hard problems for people. And because they're hard problems to solve, they take a lot of memory and a lot of CPU. And so that basically means that task queues are awesome. Oh, whoops, bad animations. Yeah, so we've got these high memory and high CPU requirements, which means that we've got different resource constraints between the web server and the workers. Perfect for asymmetric architecture. These optimizations take a while to run, and so they definitely are too long for a web request, and we can definitely wait for them to complete asynchronously. Perfect for task queues. This workflow with import, optimize, export, it's inherently asynchronous. Again, perfect for task queues. And we actually, just a nifty little extra, is we have a fixed cost support model for a lot of our clients, which means that we can just have the servers sitting there, and if they try and do too much stuff, it's perfectly fine for tasks to sit in the queue while they wait to be processed, which is awesome for us, saves us money. So yeah, basically, task queues are awesome for us. Yeah, so as I said earlier, Celery is the standard, which is why we initially chose it for our task queuing implementation. It really well supports the use case of a fixed pool of worker machines. But yeah, what we would do is we would have a bunch of machines. We would run a fixed pool of workers on our fixed pool of machines. And then we would report back logging messages as we were going, and we would save those in the database. So in terms of actually coordinating the tasks, Celery gave us enough, and we didn't need any particularly complex state tracking on top of that, but we did want to report back progress messages. So we used the database to write log messages. But unfortunately, Celery broke our hearts. Like I said, Celery has a lot of really complex and rich options that are incredibly powerful. But unfortunately, that means that there's an incredibly large set of configuration options. And to make it worse, there are 4 different ways to configure your Celery setup. And it's impossible to diagnose misconfiguration because those 4 different ways all have a lot of the same settings. And if you've got settings that interact with each other, there's no way to tell how they interact. And so you get these weird dependencies between different Celery settings. Basically, if you Google Celery horror stories on the internet, everyone will talk about, oh, wait, we misconfigured Celery. Unfortunately, I missed Brianna's talk yesterday, but apparently they even had issues with Celery configuration. So pretty common problem. What made it worse was that the defaults in Celery were not at all configured for our use case. Celery is designed for processing short tasks that, yeah, they're a bit longer than a web request, but they're really quick. And because of that, it's got a lot of prefetching defaults set up. So it'll grab a bunch of tasks, process them, and then once it's done all those, it'll grab some more tasks. And this is to reduce network communication. It makes great sense for the use case where you've got a lot of short-running tasks. But given we've got solves that run between 1 minute and 1 day, it kind of didn't really work in our favor because Celery would prefetch tasks on the same worker, and then they would never get run because we were running a day-long solve with another thing prefetched and all this spare capacity. And it actually took a surprisingly long amount of time for all of these issues to become clear. As we got bigger, people were using the workers more frequently. And so if you had 2 things queued at the same time, your worker would pick up someone else's task, and it would sit there and not get executed. But once we reached this point, we kind of were screwed. We had to do something, and Celery wasn't going to cut it. So we ended up, oh yeah, so just for your benefit, in order for our setup to work, we had to do 3 separate configuration options in 2 places. These are the settings. This is what's enabled. This is what you have to do to disable all prefetching in Celery. I will post my slides on Slack. But basically, the top 2 can be configured with 3 of the 4 configuration options, and the bottom one has to be configured with the 4th and not the first 3. Yeah, weird dependencies. Oh, and also, if you have the first one enabled, it changes how the second one behaves. Weird dependencies, like I said. Anyway, yeah, we looked at a bunch of other task queuing solutions. Crazily enough, rolling your own is actually pretty easy. If you've got a good message queuing library, you can write a simple enough task queue in about 100 lines. There's a Flask snippet that does it in 60. So task queues aren't that complex until you have to add a bunch of extra features, which everyone does. So the ones we looked at are listed there. I'll be going through them one by one. First up, RQ stands for Redis queue. It's really, really simple, like dead simple, super easy to understand. The code is really easy to read. It's really well documented. And the execution model is super simple. You can actually look at Redis and understand what's going on internally because the structure is that simple, which makes it really easy to get high quality monitoring. So over on the slides, You can see task definition. We don't need the task decorator thing like Celery had. It had @celery.task. And you come up with an RQ queue, and you add your task to the queue. I think that code's wrong. That's bad. Yeah, so what the code actually should read is that first line should be queue.enqueue at brackets add 1, 2, and then everything else is exactly the same. I've used this os.system shorthand here to demonstrate you just run this stuff on the command line. So all you do is write RQ worker, and then whenever it receives a message with a task, it'll import the task from the correct location, which is why you don't need the decorator. It just goes and uses Python's import system. Yeah, Huey. Huey it builds itself as a little task queue. It's got a lot less code than Celery, and it's a lot simpler. But it actually has pretty much all of the same features. The one you do lose is it only supports Redis and SQLite, unlike Celery, which supports Amazon SQS, Redis, AQMP, the RabbitMQ queuing protocol, and some other stuff. And it has a kind of nicer task chaining API than Celery. If we have enough time, I will show you the task chaining stuff. It's really cool. But yeah, otherwise, pretty much all of these are very similar. You have decorator, and then in Huey, by default, they're always, the default call will be asynchronous, whereas in other libraries, you have to specify that you want the asynchronous call. And it's got the same .get API. Dramatic, again, basically the same, except you've got send instead of delay, and you don't have to wait. This call will block, which is less than ideal. Again, you just run it command line, except this one you point to a module path, and that module path is used to configure your dramatic actors. This one has RabbitMQ and Redis support, but terrible docs. Basically, if you want to do anything beyond just sending a task, it's not fun. Task Tagger. Task Tagger is actually really cool. It was the first library I found that did distributed locking. I found this before I found Huey. Distributed locking is where over all of your different workers, only one can enter a section at a time. And it actually provides a bunch of extra queuing primitives, which are really good. And it's architecturally really solid. It just supports a lot of stuff that makes failure less painful. Unfortunately, all you can do is find out your task is done. You can't find out any extra information about that. You can't find out if it failed. You can't find out what the result was. But again, API is exactly the same as everything else. They're all really simple, which shows that Celery did a pretty good job with the simple stuff, because they pretty much all copy the Celery API for defining a task. And then Dask. Dask is a bit different. So Dask is a project by the PyData Foundation, the same people behind SciPy and NumPy. It's not a task queue, but it does really well solve the data parallelism in Python problem. So instead of a queue, it's got a scheduler that you run over your entire cluster, and it's designed to distribute pandas data frames and NumPy arrays over your entire cluster to let you do your processing. And it actually implements all of the scikit-learn APIs in a distributed fashion, which is absolutely awesome. It does also have a task queuing-like API, but it uses the scheduler to distribute those tasks. So if all you want to do is run your work somewhere else and you happen to be using pandas and it's super big data sets that you use in clustering, check this out because it's really cool. Yeah, so that's the list of task queuing APIs. This is where we are now. We're running RQ in place of Celery for most of our applications. The ones that are still running Celery are the ones that I haven't gotten around to porting over yet, and it's actually very easy for us to port. RQ is so simple that we were able to actually implement Windows support for our limited use case. It doesn't have Windows support by default, but now half of our developers who run Windows are running RQ. And it took less than 60 lines to add Windows support, which is pretty awesome. And our tasks never get stuck in the queue while we've still got capacity available, which is a big improvement over Celery. So we love RQ right now. It's great. I already covered all that. Oh yeah, we were already using Redis for caching, so it made a lot of sense to use something that used Redis as a queue as well. And so far we haven't really had any issues. Did I miss anything else? Nope, it's simple, it's great, it's lovely, easy to understand. Yeah. So the conclusions there are task queues are really great. They give you architectural flexibility, but the only cost is stuff you should be doing anyway if you're doing scale web systems. And they're super relevant at the moment. Like, everyone uses task queues. Other takeaways, Celery is really powerful but complex. If you're not using any of the complexity, you're fine. You won't have to worry that much. But as soon as you do anything beyond their default use case, you're going to have to do some research. And it's important to know what you need from your task queue. Because if you do, you can realize that Celery is too much and too complex a burden and switch to something tiny and simple, like we did for RQ. It's probably a generally good takeaway to know what you need for any piece of infrastructure anyway. But there's a lot of complexity in the standard solution in this particular case in Python land. So especially relevant here. I guess questions.
Beautiful. Thank you, Tom. We have some time for questions. Does anyone have any questions?
You were going to show us that task chaining.
Oh, yeah,
API?
bonus content.
Awesome.
Yeah, lucky you. Yeah, so that's task chaining in Celery. It gives you two different APIs for it. And when you do add.s, that represents a signature of add partially applied with those arguments. In this case, add takes 2 arguments, so you don't provide any extras. It generates the result and passes it on to the next one, and generates the result and passes it on to the next one. And to actually trigger that, you just call, and then you get a normal task result, but internally it does all the chaining for you in the system, which is pretty cool. And then it's also got the binary or pipe operator you can use as well. So that's Celery land. Huey's on here as well. I like the .then APIs because I'm a Haskell guy, and it makes me feel like I'm using monads even though I'm not. So yeah, again, pretty simple. You do the signature API, .then. Yeah, and then distributed locking. So this is code directly stolen from the Huey documentation. On the bottom 2 lines, you see with huey.lock task db backup. Means only one task can enter there at a time. Yeah, distributed locking is actually surprisingly easy to implement if you have something like Redis, because you can just have a key there and say, you can use Redis primitives to effectively do locking on that key. Yeah, that's the bonus content.
Thank you for your talk. Quick question: did you guys try to engage with Redis? With Celery dev team? Like
nope.
About your no. All right. Fair enough. Fair enough.
They probably have better things to do, and it's very clear that they've designed it for the most common use case, which is not ours, and changing the defaults does not make sense for them. So just finding those configuration options was great for us. But what actually killed us was it turned out there was a bug in the SQS implementation that meant that one of those was ignored, and it meant that our stuff was still getting stuck. So that bug has since been fixed in a more recent Celery version, but by the time it was fixed, we'd already moved to RQ. So.
Great talk, thanks. One quick question I had is, in the past I've used Celery, and when Celery is distributing the tasks, it has to, I think, pickle them.
Yes.
Are there any restrictions on what can be sent as a task with RQ?
We didn't have to deal with that. So because of the restrictions that Celery provides you, we'd run into a lot of issues. And I actually ended up implementing our own serialization layer on top of that, because there's no easy way to flexibly extend the existing serializers without defining your own. And we just wanted to use bog standard JSON to serialize stuff. And so what we ended up doing was converting stuff into stuff that was JSON serializable and passing that in. And we just reused that exact same logic for RQ. What I'm pretty sure RQ does is it also just pickles, but we didn't need to deal with that.
We're looking at using Celery at the moment, and some of the features that we like about it are that it's got a scheduler add-on, Celery Beat, and Flower looks like a really nice monitoring tool for Celery. Are there any similar scheduling and monitoring things for RQ?
Pretty much all of the task systems I listed have some sort of scheduly type thing. So that distributed locking thing from Huey, it has the oh wait, wrong direction. Yeah, so that actually has Huey using periodic tasks straight up, so effectively you get scheduling off the bat. RQ has one, Task Tagger has one, Dask has one. Everything has that. Remonitoring, Celery has a pretty nice monitoring dashboard, and it's a lot easier to build your own monitoring tools because you can actually understand what's going on in the internal structure. We actually had some issues with the Celery Flower thing at some stage. That was before my time, and Mitch did that. What were the issues we ran into? Didn't work. Didn't work. Okay. Okay, this was 2 years ago that we tried that out, and we basically gave up on it and did a tiny bit of state tracking ourselves. And it was enough that we didn't hate our lives, but it wasn't great. But RQ is just nicer so far because it's simple. I think that answers your question. Yeah, cool.
Hi, thank you for the talk. And we are using the SQS as the backend of the Celery. And when you do something like retry, it's a nightmare. So I'd like to know when you switch from Celery to RQ, do you happen to have some experience on the retrying? And I feel mostly retry exception.
Yeah, so we actually mostly avoided retry. It's not too hard to write your own retry for any of these task queuing systems because they do generally provide enough that you can just catch your exceptions and manually write retry. But who wants to write manual retry with exponential backoff? Basically, none of our tasks suited retry, so we never actually had to use it. We just manually reported the failure and relied on the user determining whether or not to retry. Because if, in all of our situations, if it failed, there was an issue with your data. So, sorry, I couldn't help more.
What kind of tools are you using to monitor tasks to be able to tell how many failures, how many successes, and so on?
So in RQ, they provide a dashboard that tells you, RQ actually, when your task fails, it moves it onto a failed queue and then provides a one-liner script that moves all failed tasks back into their original queues, which is cool. But it also has retry straight up. In terms of monitoring, we actually directly report these failures to the user because, like I said, if something goes wrong in one of these, it's almost certainly your data's wrong, for our use case at least. But yeah, the dashboard is really nice. You can get reporting straight up because it sends messages when it puts stuff in the queue. So,
is it something similar with Flower in Celery, or?
Like I said, we tried it before my time and it died and it didn't work. But Celery does have an event system, and that event system will give you messages every time the state of your task changes, which is actually really useful. RQ is a bit different in that it provides, in Redis, you've got the up-to-date state of the system rather than an event streaming system. So yeah, but the event system in Celery is actually quite cool. Huey provides the exact same event system, basically. Huey is Celery, but with less complexity and simpler code.
We probably have time for one more question, if there are any further questions.
The question is really, with the message queue systems you're using, which of those scales to millions and millions of tasks?
All of them. So Redis has a lot of complexity in scaling to huge numbers because it's designed as a key value store primarily. But RabbitMQ and Amazon SQS are both designed for massive scale message passing, which is kind of the use case Celery absolutely excels at. If you're doing millions of tasks in flight constantly, you probably want Celery, and it's worth the overhead of spending those hours working out what configuration options you need.
Beautiful. Well, thank you very much for your time, Tom, this afternoon. Can everyone give him another round of applause? And as a token of appreciation, enjoy this mic.
Thanks.